Hello, Mr. Den here. Welcome to Physics, Chapter 2, Section 3, Falling Objects. Today, our objectives are going to be relate the motion of a freely falling body to motion with constant acceleration. We also want to be able to calculate displacement, velocity, and time at various points in the motion of a freely falling object. Before we get too far into this, let's establish some crucial concepts. First off, free fall is the motion of a body when only the force of gravity is acting on that body. The force of gravity causes objects to fall with a constant acceleration. And then another thing we need to keep in mind as we work through these problems, if air resistance is ignored, objects near the surface of a planet fall with the same acceleration. However, our everyday situations, there is air resistance, but we are going to assume that air resistance is not there for the sake of making these problems a little bit more manageable for us to work through. On the Earth's surface, the acceleration due to gravity is denoted with the symbol A sub g or just the letter G. And the letter G, or lowercase g, is specifically referring to gravity on Earth. So like when you hear when they say things like G forces, that's what they're talking about, is an acceleration that it would be equal to what is the Earth's gravitational acceleration. The magnitude of G is going to be 9.81 meters per second squared. And then the direction of G is downward toward the center of the Earth. Now, one thing we need to make sure that we remember to do as we do these problems is make sure we have the correct sign as far as being positive or negative. Now, the reason this is important is because you always have to have, with vector units, you need to have a way to indicate the direction. Now, so far we've been using positive or negative. Now, sometimes you can just say up or down. However, when it comes to doing the math portion of this, you need to keep the signs correct. So, because our usual way we set problems up would be using a coordinate plane, and since the typical coordinate plane that's used has y on the y-axis, and so that's going to be one difference in these problems. Instead of change in x, we will call it change in y. But on the y-axis, up is the positive direction and down is the negative direction. And since the acceleration due to gravity is pulling something downward, or it's accelerating downward, the G is always going to be equal to negative 9.81 meters per second squared. Now, earlier I said in the absence of air resistance, objects are always going to accelerate at the same rate. And so this picture kind of shows how this is happening. And so you notice we have a feather and we have what looks to be an apple. Now, this picture is multiple images taken over the same time frames. So, for example, the first apple and the first feather right here, this is what they were both taken at the same time, and then 1 second later or one part of a second later, it's the same amount of time takes place between each set of images. And so you notice that they fall at the same rate, and the space in between is getting bigger and bigger, which tells us that they are going faster and faster as time goes by. Now, some of the problems we deal with free fall, we will have an object that has an initial velocity upward. And so something that we need to be mindful of is that this acceleration due to gravity is always acting on that object, and it's always downward. So if you look at a set of images here, and again it's similar to the picture we just looked at, and all of them, same time frame in between each. So as the object is going up, its velocity is going to be positive. However, the acceleration is negative as it goes up. That's why we see smaller and smaller spaces in between each one. It's slowing down. Now at some point, the velocity, when it gets to the top, for that one instant in time, velocity will be 0, but acceleration is still going to be negative. And then as we start to go back down, acceleration is still negative. In this case, velocity is also going to be negative because it's going down. And then as it goes down, it's going to speed up, thus the bigger spaces in between the pictures. Okay, so let's go ahead and try to work our first problem. And so again, I think it's important that we try to find the givens first. So straight away it tells us that we have initial velocity of 6 meters per second, because Jason, he's hitting the volleyball so that it moves with an initial velocity of 6 meters per second. So I already have that identified, and this is upward, so therefore it is a positive velocity. And if the volleyball starts 2 meters above the floor, how long will it be in the air before it strikes the floor? So this is a really important time to go ahead and establish your coordinate system or your frame of reference. So if we were to draw a line here at 2 meters up, so this is 2 meters from the floor. However, we're going to call this the 0 point or the origin on the y-axis. I know my line's not very straight, it's kind of slanted actually, but you get the idea. So that means this distance from here to the floor is actually going to be -2 meters. So we would call the displacement here -2. Now it says x here, but actually you'll see this written in examples as y, so change in y. And it's not really important when you're doing this whether you call it x or y, but you need to be mindful that it is on the y-axis, so we would call that y. So we've established what the displacement is going to be. And then because this is taking place on Earth, the acceleration due to gravity is going to be -9.81 meters per second squared. And we don't know the final velocity and we don't know the time. Now what we're being asked to find is, it says how long will it be in the air before it strikes the floor. So we're being asked to find time. So that's what we are going to focus on. Now this is something that I noticed some of us are not doing a great job of. We're not paying attention to what we're being asked to find. And so we end up doing some work that we waste our time because we're finding something that is not even being asked for. And so now before I told you it's a good idea to identify which formula to use. Now sometimes you can't just pick one. Sometimes you have to do a multi-staged plan here. And so when you first look at this, it might be tempting to go for this one right here where we have, because I have a VI and I have a change, no I don't have a change in time so I can't use that. Well actually, since that's what we're trying to find, I have a VI, I have a change in position, which this would be change in Y. Anyway, so I have a VI, I don't have a time, so it might be tempting to use this. But the thing I think, the reason we can't use this is because it's given an initial velocity and we don't know that that velocity is a velocity that's going to have this ball traveling the same distance up that it's going to end up falling down as far as its -2 meters. And so therefore we can't use this because this kind of assumes that with this 1/2 acceleration part. So we cannot use this one. So we're going to have to find the VF first, then use a formula that where we would find change in time. And so the one that's going to work out for us is where we're finding VF down here. This will work because I have a VI, I have an acceleration, and I have a change in position. So that's the one we're going to use first. Okay, so I already have that written up here. So let's just go ahead and plug numbers in where they go. And so we don't know VF, so I'm just going to leave that blank. And then since my VI is 6.0 meters per second, and that will be eventually squared, and then that's going to be added to 2 times our negative 9.81. That's going to be meters per second squared. And then we have our change in position is going to be negative 2 meters. And so if we go through that, we should get 75. If we do all this math, we're going to get 75 meters squared second squared. And we still have VF squared over here. And so remember, to get rid of that squared, we have to take the square root. So velocity is going to be 8.7 meters per second. Now, here's one of those things that we have to be mindful that what is occurring here, because remember, we established our origin here, and so the initial velocity was up and our final velocity is going down. And so even though we didn't get a negative coming out from underneath that square root, we are going to make this negative. So our velocity final is going to be negative 8.7 meters per second. So now we're going to use that final velocity and plug it into the other formula that we identified earlier. So I'll go ahead and we can just plug things in where they go. So we got negative 8.7 meters per second is going to be equal to positive 6 meters per second plus our negative 9.81 meters per second squared, and that's going to be multiplied by the change in time, and that's what we're finding here. So we can go ahead and move this over via subtraction. So if we do that, we're going to have, if we subtract 6 from negative 8.7, we're going to get what? Negative 14.7 meters per second, still equal to negative 9.81 meters per second squared times that change in time. And then we could divide both sides by negative 9.81. And I'll go ahead and write the units over here. And so what should come out of that is seconds will be the only thing left after we cancel units and whatnot. And we should get a change in time is going to be equal to 1.49 and some change here, 498 seconds, and then we will go ahead and round that to proper sig figs. Oops, that's not what I meant to do. 1.50 seconds. And that seems like a reasonable answer. Okay, so let's move on to the next problem, and then we'll end this screencast. So again, we have we're still dealing with a falling object here. So on Mars, a robot probe drops a camera off the rim of a 239-meter cliff. The free fall acceleration on Mars is negative 3.7 meters per second squared. We want to find the velocity with which the camera hits the ground. Okay, so again, we would want to go and identify our givens, always being mindful of the sign of what we're finding here. And so here's our origin, and so we're working in the y-axis still. And so this would be positive and this would be negative. So since we have a 239-meter cliff and the origin is at the top of it, and so to fall down, that would be a negative 239. So negative 239. And acceleration due to gravity is negative 3.7 in this case, because we are on another planet that doesn't have the same gravity as Earth. So that's why that's different in this problem. We don't have a time, we don't have a velocity final, and that's actually what we're trying to find. And since it's dropped off the cliff, that means VI is 0 meters per second. Our answer should be negative because it's going down. So we need to always be mindful of these kinds of things, and so that way at the end we can sort of we can self-evaluate our work. So I'm gonna go with so we need something that has velocity final, and we have displacement, and it looks like I'm going to go with this guy right here because we have an acceleration, we have a displacement, and we're trying to find that, and this works out perfectly for us. So VF squared is going to be equal to 2 times negative 3.7 meters per second squared times our negative 239 meters. And so we do the math, we're going to get 1768.6, and that's going to be meter squared second squared. And then we still have VF over here under VF squared, so we have to square root this. And so velocity final is going to be 42.1 meters per second. And that's a positive answer we got here. But again, we have to just be mindful of what's happening here. It's falling down since our origin was up here. The going up is a positive velocity, so we will go ahead and change that to 42.1 meters per second. All right. So assignment for this section, and this is actually the last section of the chapter, so that's good news. So we're going to do the worksheet 2F falling objects, and then you will have a quiz over 2F falling objects, and then you'll be doing the quick lab on page 62. I'm going to have you design your own experiment, and pretty much you're going to follow that, but you're going to pick your own groups to compare. You need to come talk to me, and I will give you the things that I need you to turn in for that assignment. And then once you have those two things done, you will be ready for the Chapter 2 test. This concludes this screencast. I hope you enjoyed this as much as I enjoyed making it. I will see you in class.